Okay, sorry for the delay. So I think that in that case we try to continue without a break. Yeah, so unfortunately. So we start a new topic, which it looks like I'll be giving all the lectures until the test, like 4 lectures about this. It's initial value problem for the is. For ordinary differential equations. By the way, we agreed about the test, right, on a Friday, June. Oh? Yeah, 3rd, no, it might be, probably. So I think it should last like 3 hours. So if we start normal time, 3 hours from a normal time is okay for everyone? So I will just ask if this auditorium is available or not. And so you just prepare all these topics that we did, look at the exercises. I think I'll be close to the book. And that's fine. So we consider ordinary differential equations. So which is y dot equal f of ty. So here dot is usually, so y dot is derivative with respect to t. So usually we consider ordinary differential equations, we have in mind the evolution. So time is t is usually we refer to call t time. And y is a state of the system which is so y is usually okay. So it's in vector in d-dimensional space, or in often it's just in some domain inside d-dimensional space. And so we consider initial value problem. Initial value problem is a equation plus initial condition. So let's put initial time to 0, so it doesn't matter that much, and y0 is initial value. So we want to find solution. So solution is a function. So we look for a solution. So it's function defined on some time interval, which includes 0 until some time, including final time or not including final time. So here f. So f is a function which is from time. Time is real. Time in that case is some interval. Y is this, let's say this domain where the system is defined, and the derivative is in a linear space, so it's in Rd. So solution is a function which satisfies both relations. So first relation for all times, and the second relation for initial time. Right? So I will recall you some theorems from ordinary differential equations that you study in the course. I will not give exact formulation. I'll give almost exact formulation just to give an idea what is important, what is not. So usually there are 3 issues about initial value problem, which are so very basic. First, existence of the solution. Second, uniqueness. And the third is this existence uniqueness is local in time, so just or global for any time. So all of them have implications also from point of view of application. Non-existence is fundamental. Uniqueness or non-uniqueness both can happen, actually in different applications. And global, and if it's not global in time, it's also certainly trouble. So the first is existence. So for the existence, so the local in time existence, so if f is continuous, then there exists a local in time, which means for some positive time. So for some, if there is some interval from 0 to some positive value, solution. This local solution. So solution of the initial value. Let's initial value problem. So continuity is just enough already to have a solution, but the observation that it's in this case it's not necessarily unique. So let's give you an explicit example. Not necessarily unique. And then we consider such example, like I usually take example from which has meaning in fluid dynamics. So let's consider example of this type, 1/3. 1/3, and we start at the origin. So what do we have is that we have the function which does not depend on time, so only depends on y. Y is real. Or in that case, we can just consider positive. And then we start at 0. So no, first of all, this is a function. So function is a cubic root. So function is like this. And certainly not, it's continuous, not differentiable, right? At 0, not differentiable. So what is the solution? So you can check that actually all solutions that you can define, they have the following way. So they are 0 until certain time. And the expression that you find using this separation of variables, it's t minus t star over 3 half. So this is for t star infinity, and this is for any t star. So what this solution means is that so this is solution y, this is time. Solution means that you start at 0, but 0 is also solution. So what solution can do is the solution can stay just exactly at 0 until a certain time, and then from that time spontaneously depart along this solution. So this is a solution. And this time is arbitrary. So you already directly see that there is infinitely many solutions because of the singularity here at 0. So it's continuous, not differentiable, infinitely many solutions. Okay. Another thing is that also maybe not global in time. So for not global in time, we can just give us an example which is completely regular. So y dot equal y square. Let's also start. Let's start from 1. So what's bad about this equation is that y will increase, but here it's y squared, so it accelerates every time faster and faster. And you can check that the solution of this equation, it's unique, but it has a form, 1, 1 minus 2, t. This is the solution. So it goes to infinity as time approaches 1. So this is what's called blow-up. The solution explodes in finite time. Okay, so this is the first part. So the second part is, so this is existence is important. Usually we also have uniqueness anyway, at least locally in time. Not always, but so the uniqueness comes from one of these conditions which is classical is a condition of Lipschitz continuity. So the function f ty is Lipschitz continuous if you Lipschitz continuous, so in some domain, for example. So if the difference between its values at 1 so in this case it should be independent. So if the distance of the two values of the function at two different points, y tilde is smaller or equal than L y minus y tilde. Okay. So for some what's called Lipschitz constant, positive number, which is independent of y tilde t. This is a big, vague definition. But so what I wanted to write is that the function is Lipschitz continuous in certain domain. If this is true for any y t tilde in this domain with fixed L. Okay. So then there comes a theorem. Usually it's called Picard. Can have more names. So the Picard theorem tells that the solution of the initial value problem for with the function I think it should be here. I may check it later. I never remember. So it's which is continuous with the continuous function. Let's take with continuous function, which is also Lipschitz continuous. I think this should be enough. So it should be continuous with respect to time and y. Then you have existence. And then it's also Lipschitz continuous, and it gives uniqueness. So the solution of the initial value problem for is unique. Okay, so if there is a solution which is guaranteed by the previous theorem, then it is unique. In the region where it exists, yeah, because then there is this observation that it may not in principle exist for infinite times. And here the simple observation is what is this Lipschitz condition. Lipschitz condition is a somewhat weaker form than differentiability. So what you can say that if function is differentiable, continuously differentiable, then it is Lipschitz continuous. Continuous in any compact domain. So essentially why is because if you take any domain, and then you can just take L to be maximum derivative. Maximum derivative in case of when y is a vector, it's you take it you have a matrix of derivatives, and then you take a norm, the operator norm, and it gives you L, which this equation will satisfy. So the proof is not that direct, but essentially the idea is this. So and the final observation, so final theoretical part before going to the numerics is that why I consider equation in this form with one derivative only. Because normally many equations are not in this form. You have two derivatives. Like in mechanics, you almost always have two derivatives with respect to time. So the reason is that you can always reduce the system of equations which explicitly resolved with respect to higher order derivatives to this form. So we can reduce ordinary differential equations with higher order derivatives to the form this form. So I'll just give example which will make it, I think, very clear. Example, so take two equations. For example, we can reduce systems, right? Systems of ordinary differential equations. So let's take a system. One will be second order. Let's say it will depend on x and z, and the same second system will be, so let's take G1, and this is G2. And it will be z 2 points x point. So that's a nice system. Two equations and a lot of derivatives. So how you do in order to make a reduction, you have to resolve each equation with respect to highest order derivative, and then give them new names. So you take vector y, so it's free derivative plus 2 plus 3. So you take first component x, the second component x dot. You see, the higher derivatives are not necessary because they are already given by equation. And then for z, we need z dot, z, and second derivative. So this is y. And then what you can clearly see that what is y? Y dot, it will be x dot, x double dot, z dot, z double dot, z triple dot. And then substitute them. So x dot is y2. X double dot is G1 of x. X is y1, z is y3. Then z dot is y4, z double dot is y5, and z triple is G2, z double dot y5, and y2. Okay. So you see, this is exactly what our f of ty. So it only depends on y. So this is how you always do. So whenever you have a system and you want to solve it numerically, all the most of the methods, they are done for this kind of formulation. So what you do, you do this reduction. Sometimes you have to do it in a clever way, especially if your system has some conservation laws that you want to be satisfied also in a new formulation, numerically. Okay, so this is it. This is it. So now we want to solve the system. So what we will do is we assume that there is a solution. So assume that y of t is a solution in the interval between 0 and t. And now, so this is timeline, starts with 0 till t. And so what we will do is we will first use a uniform mesh. Yeah, so numerically, we want to know this solution, and we can represent it only just in finite number of points. So we divide the interval into the subintervals of size h, and if there are n intervals, so we take h equal t over n, so n intervals, and then we define, so we can define time. So t0 is 0, t1 is h, so tk is kh, so until the tn is t. So we divide. We take this uniform sequence. So we want to compute the solution yk, which will approximate the solution at each time. So this is what we want. So we want to we put uniform sequence of uniformly distributed points, uniformly spaced points, and we want to compute numerically what is the value of the solution at each point. So so far we consider uniform mesh, but it's not necessarily uniform. So it also can be adaptive, but we talk about this later. Okay, so we start with the first first method is Euler method. This is a very fundamental thing, but rarely used. Sometimes you can still use it, but at the same time it's something very simple to do. So what you do is that you have a equation where the left-hand side is derivative. Right? So what you do is take a derivative at any point tk, and you approximate it by the definition of the derivative. You take y of tk plus h minus y of tk divided by h, right? And now each of these points we are going to approximate by these values that we want to compute. And on the other hand, this we know what it is. So this should be on the other side. So let's write it here. This is exactly f of tk. No, let's just write it normally. So on the other hand, y dot of tk should satisfy the equation, so it will be tk y tk, and this is approximated by what we expect yk, right? So now the two equations can be matched. So which gives you exactly the Euler method. So you put h on the other side, yk to another side, so you give the new point in terms of the previous point. So this is Euler method. So this is very intuitive, because what you do, so you have derivative. So every next point after step h should go into the direction of derivative, which you approximate from previous point. So this is absolutely clear. So now let us compute. So what is the difference? What is the error? And error means that what is the difference between between approximation and exact solution. So what is the difference? So the next step is what we compute the difference. So now, in order to formulate the theorem, so we suppose that, first of all, we make certain assumptions. First of all, about the norm. So we will need to match, I wonder why. Okay, so suppose that f is Lipschitz continuous. So constant L, so we know the constant of Lipschitz continuity, and then we also suppose that the M is maximum. So you can take a maximum of the norm of the second derivative. Okay. At all times of our interval. So it's finite. Oh no, it's obviously finite. So it exists and finite. Exists and finite. Exists. Okay. So exists there. Not little. And finite. So not infinite. So we assume that it's Lipschitz continuous, and then there is a second derivative. Okay. So usually existence of second derivatives, it comes from the first derivative you already have. For the second derivative, you should differentiate the function f in principle. So usually it comes from the differentiability of f. And all we need is that second order derivative has a maximum, so has certain maximum in this interval. So now we can directly give the formula for an error. Theorem. The theorem tells you that maximum for all points of our approximation between approximation and solution, so between Euler method approximation and solution, is not bigger than h, and then there is a branch of constants. So it should be 2m, m, 12. That's it. So so this is an error is order h. It's order h, but it also depends on the derivative, and this also depends on how large is your interval. And you see that dependence on the size of the interval is quite strong. It's exponential. So that if the interval is large, then the exponent can be huge. So h then will be very small. So this is potential trouble. But it's always there. Okay, so the proof. So essentially what we want to prove is that it's order h by the very clear coefficient. So what we do, okay, so what you do, take a Taylor expansion. Taylor expansion gives you that y at time tk plus 1 is y at tk plus h. And this is by expanding Taylor, it's y tk plus h y dot tk. We continue plus h squared by 2 y double dot. And this is psi. Okay. So what it is, it's exact. So where for some psi k from this interval between tk and tk plus 1. It's exact, and in this relation, so this is f, right? This is f tk y tk, right? So what we do is that we subtract from this relation from expression from the expression of Euler method. So what you get, so then it will be yk plus 1 on the left minus this, yt k plus 1. And it should be equal yk minus ytk plus h. And then we will have this f tk yk minus f tk ytk and minus h squared by 2 y double dot Okay, and now what we do, we take a norm from both sides, use triangle inequality. So y. So let's call dk this difference. We will call it this norm. So y k minus y tk. The difference between approximate and exact. So what you get, you that dk plus 1 is smaller or equal, and then we take triangle inequality. dk plus h norm f t yk minus f tk. No? And remember that this is h squared by 2. And the norm of double dot was limited by m. So you have m here. Now remember that this is also smaller or equal than L yk minus ytk by the Lipschitz condition, which is L dk. So at the end, we have the d k plus 1 is smaller or equal than 1 plus hl dk plus h squared over 2m so let's call this delta, is k. So what we have is d k plus 1 is smaller or equal than 1 plus delta dk plus k. And this can be continued. So this is for any k. So it means that or you can do it like this. Tk is smaller or equal than 1 plus delta. Just take k, smaller k, the same relation. And then let's use it every time iteratively. So now we use it for the next one. And so this should be smaller than 1 plus delta dk minus 2 plus k plus k, etc. So now use it for dk minus 2, so iterative. So use the same formula many times. So at the end, what you get is dk is smaller or equal smaller or equal. So what there will be 1 minus delta, and you can compute it how many times it will appear. You can already give it. It will appear exactly n times, no? And if you appear in time, the end will be the 0. So this distance at initial moment, and plus and then there will be k multiplied by such a expression, which is 1 plus delta plus 1 plus delta squared, and so on, until 1 plus delta k minus 1. And this can be summed explicitly. So this was plus k. The sum is so the sum can be estimated as exponent and delta minus 1 over delta. Check. Okay, in fact, it's written like this. It's written like, let's do it normally. So it's equal. So the exact formula will be 1 plus delta n minus 1 and 1 plus delta minus 1. So delta 1 cancels. Okay. So d0 is 0, because at the initial moment we don't have an error. The first points are exactly the same, it's initial condition. So dk is small or equal this 1 plus delta n minus 1 over delta. But now this is smaller than exponent of delta, yeah, for delta positive. This k, h, k delta. Minus 1 over delta. Okay. So now let's put back this coefficients that we all had. So delta was LH. The best thing is that I used k. It's not good to use. Let's put star to this k, because otherwise we are completely confusing. Because there is another k. This is normal k. This is k. Sorry for this. This is k. This is k. You're not following. So where is k? K is in front. K star. So now let's put it all back. So k star was h over 2m h squared. Then delta was LH, so it's 1 over LH. LT. LT, no? No, LH. HL. And then exponent was K HL. Minus 1, minus 1. So now remember that KL is small equal, KH is smaller or equal than time, yeah, because KH is an interval and K is a number of times, so it's not bigger than T. So what we get, the maximum dk over all k is small or equal than, so this h can cancel, so it would be h m over 2l exponent TL minus 1. So this should be what we needed. Hm over 2l, yes, exactly. Proved. So essentially, what we proved is that whenever you fix time t and decrease the interval, you converge. So method works. So Euler method converges, which means that yk goes to ytk as h goes to 0. So for all points, we have convergence of the approximate solution to the exact solution. So this is, in practice, this is only half of the story as usual, because in these calculations, we assume that everything was computed exactly. Yeah, so there is another side, is that there are a round of errors. So there are a round of or computational, which is when you compute right-hand side, the f, whatever f is, you may have errors which are not only round off for some other reasons. Computational errors. So what is the effect of these extra errors? And that we have to consider. So assume that everything is not computed exactly. So assume that initial condition, for example, is given with some error E0. Then we assume that function f always computed. So we need to compute it in the Euler method and these points. And this is actually okay. So always computation of the function f gives you an error. And then also what you can have is that the whole computation of the Euler equation is also not correct. So the yk plus 1, when you substitute to Euler method, it also has a round of error. So also there is error. Okay. Everything is computed with an error because we never compute anything exactly. So what is the result? So we take so let's assume that these arrows can have have the same order. So just substitute, there isn't a bound for all the arrows. So then what you can have, this is a long computation, which will be exercise. So what you can have is that you can repeat the whole computation that we did, but now taking account that at every step there is an extra error. So you have to sum them up. So what you get is that instead of that formula, you will have that the maximum for all at all points between the approximated solution with an arrow and exact will be zero LT let's put some another line. So you can see that, so this is what we had already. Right? So between this term, this product. This is what we had, and this is an arrow of the initial condition. And you see that actually an arrow of initial condition can grow exponentially, especially in chaotic systems. So this is mean that it's important to start correctly. Yeah, so that's in the sport, the initial value is very important for this reason, for some sports. So if you start with an arrow, the arrow increases a lot. And then this is an arrows, these are arrows of the round of both in computation of f and both in computation of each step in the Euler method. Okay. So what you have at the end is that how h enters. So the h enters in two places. That here and here, in the top and in the bottom, which means that if you plot error as a function of h, so when h is very large, this dominates. So error will be proportional to h, and this is the term because of discretization. We take the step very big, then Euler method is not very accurate. So at the same time, if h is very small, what will dominate is the round of error. So it's round off. Round off or computation, whatever is the bigger source. So it's never perfect. So there is always h, some optimal h, where you can achieve the best approximation. We already had this picture in the other part, I guess from linear algebra. With exactly the same philosophy. So by knowing the expression, you can estimate what is at least by order of magnitude, what is a good h, what is a good step for your method. Because if you take step much bigger, you will lose accuracy because of the Euler method. If it takes step much smaller, you will have a combination of round of errors. So that means that there is some limitations for the error that you can in principle reach. It's getting better with higher order methods that we'll consider now. But still, whatever method you consider, the result is the same. So there will be some optimal step. Okay, so now Euler method is the simplest version of all these kind of methods when they do just single steps. And usually not used. So usually we use higher order methods, which we consider now, so they will be under the name of single step. So this is class of methods, which is single step methods. Essentially, we are talking about Runge-Kutta methods. So so all these methods can be formalized within the single relation, which is initial step is given by initial condition, and then every next step is given using the previous step plus h by some function. Right? Some function which depends on three variables. It depends on time, previous state, and step. So this is for other steps. So the function is so essentially the step is defined by this function, phi capital. So the function, it should be from our interval, actually from a collection of points, right? So times, so it's not good. For the collection points times values of y, which are in Rn. And no, it's actually function. It's interval, because we take it for different h, right? So it's a full interval times Rn times R plus, and the value should be in Rn, Rd. So clearly, what is Euler method? Euler method is where the function is just this f. This is Euler. But we can have different methods. So how to construct better methods. So we just start with we make explicit construction, and then we will generalize it to already higher order method. So we will make what we derive is we will derive a second order Runge-Kutta method. So what? Consider our equation y dot equal f ty in integral form. So each equation we can just integrate this relation between two different times, and we integrate it between times tk plus 1 and tk. And the right-hand side is just integral. So here we substitute the function of t. Okay, and now the right-hand function of t, and we know that we can approximate this integral by quadrature, right? So we know it. So let's use the midpoint rule. It's already, we can expect it to give something better because it's second order. So we have using so what is midpoint rule? It's just taking this value at the middle between the two limits. So it will be h by f. And the point in between is, so So the step is, difference is h. So point in between is tk plus h by half. And then it will be y t plus h by half. Okay, so next step, what we do is we don't have this value. So the next is you use Taylor expansion. By Taylor expansion, we take y at t plus h by 2. So essentially, we use this Euler method for this term. So it will be y tk plus h over 2 f tk y tk. So what we get at the end is that approximately h. Oh, let's put it on the other side. So just repeating the whole stuff. So what is important is that this is exactly this function, because this function only depends on previous time, tk, on previous value, and h. So that's single step method. So we just write what is the function. So that means that the new approximation scheme method is well, I will not repeat, so I will just repeat the function phi. So this function, which gives us this expression, when we substitute here, and you get this expression, but with ytk substituted by yk. So this expression becomes as an approximation if you call this is phi. It will be h f so something more complex than Euler. So we will see that this is what's called second order Runge-Kutta. So now we can generalize the concept of inaccuracy now for the second order method in a more general way. So the first definition, which gives you what's called order of accuracy. So a single step method has order of accuracy P if the difference between the exact step, so if you take step h in exact way and subtract what would be approximated by the method. So this is exact minus approximate, so it should be order HP plus 1. So here it's important to have plus 1 for order P, because number of steps is inverse proportional to H. So if one step gives you HP plus 1, then you can deduce that summing from them from all steps, it becomes HP. So that's what, for single step, it's you add 1. Because what you compute, in fact, is not single step, but the n steps. So T over n, T divided by H steps. So this is order, and then another definition is also, which you usually want to have, almost always. So which we want to have is that the method is consistent if, so the method is consistent if what we need is that when the step becomes smaller and smaller and smaller, right? When the step becomes smaller and smaller, this should become closer to the correct value, and this means that this phi should go approach derivative. Here I implicitly assume that there is continuity in H, but this is always the case. So for Euler method, so what we have, we just compute this. So let's compute. So y t plus h minus y of t plus h f ty. Well, so this is use Taylor expansion, and you obviously so use Taylor. So this is first and second Taylor term. So the result will be h squared. So it's order 1. So Euler method has order 1. And also it's obviously consistent, right? For all it's consistent because essentially it's already the function. And the second order Runge-Kutta, well, already from the name you can see it should be second order, right? So what we do, we take phi t y h, and then let's expand it. So this is, we use Taylor again. But now we use Taylor in different coordinates. It will become f of ty plus derivative with respect to t. So all derivative, we write it, they all be at the initial point. So you take expansion as a function of two different variables. So the first will be the partial derivative df dt by h over 2. Then there will be partial derivative with respect to y. With respect to y, and then it should be multiplied by h over 2f. Okay. So you have it f ty plus h over 2, and then collect everything. So it will be ft plus f, fy. Okay, plus h square. And then it remains to see that this is exactly, so h over 2, this will be exactly derivative in time of the expression if you take y as a function of time. Because you see that this will be derivative, you should differentiate first with respect to the first and then with respect to y, and y dt, it gives another f. But this is, we know that this is y dot. So that gives you f ty plus h over 2 y double dot plus h square. Okay, so this is first part. We're finished. Nobody's coming. Good. And the second part is, now let's just substitute this expression into the condition. Which one? This condition. So take y t plus h minus y t. This, and so we, and then let's make expansion. So let's first expand the second. Here's h. So let's use Taylor expansion here as well. So for the first will be y of t plus y dot h, right? Plus y dot h is what? Is this h by derivative, which is ty, and plus h square over 2 second derivative, and higher order terms, and minus what is written here. Now h by f, h square by half y double dot square. So everything cancels. Only these are all certainly different. So this. So it's multiplied by h, so it becomes 3. So what we see is that order, or the second order Runge-Kutta method, naturally is second order. So this is why it's named second order. Okay. And also it is consistent. The consistency is rather clear because when h goes to 0, so it becomes t, y, and that's it. So it's also consistent. Okay, so I think we're done. So I'm sorry again for the delay. So thank you.